Okay, in the first video I showed you how to use the frequency function to get sort of a histogram looking output for the counts from background radiation in comparison with a black shale that's fairly high in uranium taken from near Berea, Kentucky here. So the first thing I'm going to do is test the normal distribution. What percentage would I get less than or greater than a certain test statistic? First, I need to get simple statistics calculated. I need my sample size. And I need my average. And I need my standard deviation. And I need that for both data sets. Alrighty, so the function is called norm.dist. There's an older one without the dot, but so what we want to do, I'm going to say equals norm.dist, and my test statistic, I want to see sort of the overlap of the background with the lower end of the shale counts. What percentage would be better than the larger than the low end of the shale counts? So my test statistic is 30. My average is the 22 point something, standard deviation 4.6, and I want the cumulative distribution, so I say true, and so that's 0.95 or 95% and a bit. Now norm.dist, unlike the table we've used in class, the norm.dist function gives you the area under the standard normal curve from negative infinity to your test statistic. We want what's greater than our test statistic, so we're going to say our area, 1, the total area, minus my area negative infinity to this test stat, that equals the fraction greater than 30 counts per minute. So equals 1 minus 0.95, or just under 5% would be expected to be an overlap. So now we want to see what percentage of our shale counts would be expected to be confused with background. So same thing, norm.dist, open paren, my test statistic is 34, my mean is 48 or about 49, my standard deviation 6.8, and true. And now this is the area from negative infinity to 34, so that is our result here. Just over 1% would be expected to be down overlapping with the background. Now let's use some of our built-in functions from the data analysis add-in that you've installed. What we want to do first is the f-test, see, test for homogeneity of variance, and so let's first make sure we want to enter our higher standard deviation first, and that'll be the shale. So There's the shale. And there's the background. We have haven't highlighted the labels. Our alpha 0.05, that is 95%. Let's put this up here and say OK. Alright. Our F-stat calculated is 2.2. The critical value is 1.5. So our calculated value is greater than the critical value. That means these variances are, we have to consider that they are unequal. That's a little surprising. They look kind of similar to me. But now let's do the t-test. Once again, this is the type 2 comparison of means. And we want to do a two-sample t-test assuming unequal variances. And so we want our, let's get up here, there we go. We'll put our, it doesn't matter this time, but we'll put our shale in first, and then we'll put in our background, and our hypothesized mean difference will be 0. Our output range we'll put right here, looks okay, and that looks alright. We say okay, and so here's our output. Our t-stat is 26.2. That's pretty darn big. So we'll do a two-tailed test. We are really only interested in the upside, but most often we do a two-tailed anyway. So the probability of getting that t-value by accident is something like 10 to the minus 49th. Our critical t for a two-tailed test is about 2. So these means are in fact quite different. Just for fun, let's do it assuming an equal variance and see how they compare. So let's put our first one in. We'll go up here and highlight our shale data. Then we will highlight our background data. Hypothesized mean difference is 0. Our output range, well, that looks like a good place to put it right there. And we say OK. And here, so our t-stat is 26.2. Pretty much the same. It's the critical t is different in the third decimal place. Our probability is a little bit lower, 10 to the minus 49th versus 10 to the minus 53rd. Not greatly different. The assumption of unequal variance gives you a slightly more conservative test, but in this case they're not really very, very different. So, okay, I think that'll do it for this video.